Now we are going to record the Zoom meeting as always. So please turn off your camera if you would like not to show up on the recording. And today our first speaker is Alysa Rogers. Alysa is a senior at Greenwich University, finishing her BS in physics. She has previously been involved in the research at the University of Chicago during a summer REU in 2020, and interned at the Center for Astrophysics during the summer of 2021. She grew up in Boulder, Colorado, where she learned a lot of the outdoors and continues to run and climb in her spare time. She also coaches a youth recreational climbing team at the local gym. She will be starting the University of Wisconsin-Madison physics PhD program in the fall. So the floor is yours, Alysa.
Thank you so much. Let me share my slides. Okay, thank you all for having me, and thank you for coming. I'm really excited to be here to talk to you about searching for offset AGN using gravitational lenses. Okay, I just want to start with this image. This is from one of the earliest surveys of lenses, and they found 22 new lensing systems, and you can just really see the diversity of lenses that we can observe. So we're specifically looking for quad lensed systems. We'll talk a little bit more about that later. And the first lens quasar discovered was Q0957. We have two images of the quasar, A and B. And image G is actually the lensing galaxy of the system. So only image A has this jet coming off of it. So looking at this image, you can't really tell that this is two images of the same thing. But when we look at the optical spectra of the quasar, we can see that they are remarkably similar. And when they actually looked at the spectrum of image A and then image B, they thought they had forgotten to move the telescope, but they didn't. These are just the spectra of the same object. So we'll talk a little bit more later about why we see that structure. But when we're observing lenses, what we're really looking for are offsets in our observations and hopefully finding offset AGN. So this image on the right here is just an example of a really obvious offset. So we have images A2 and B2, and then A1, B1, C1, and D1 are two sets of images of the same object. And I will talk later about why we see two images versus four images. This is just a good example of an obvious offset. And when we're looking for these offsets, we're hoping to find binary AGN, which are two AGN at the center of merged galaxies. And those AGN are going to be emitting from different positions. So hopefully we'll be able to find those emissions. And we're also looking for displaced supermassive black holes, which is a little bit later on in the evolution where the AGN and the black holes have merged. And that merging is going to kick the black hole from the center of the AGN. And again, that's going to be emitting from a different location. And the reason we're looking for these two things in particular is to try and measure the frequency of galaxy mergers throughout the history of the universe, because this is a really integral part to galaxy formation and evolution, and will hopefully give us a better idea of the formation of large-scale structure in the universe as we measure the frequency at different redshifts, so looking at different points in the universe's history. These offsets can also be just complex structure, so something like a relativistic jet. And we're not going to be able to really tell the difference between these, but we're hoping to find some offsets. So an active galactic nucleus, as you might already know, is one of the most powerful objects in the universe. These are powered by a supermassive black hole at the center that's actively accreting. And the mass of that black hole is going to be millions to billions of solar masses. And as matter accretes into the black hole, the gravitational potential energy is going to be converted into kinetic energy and electromagnetic radiation. Some matter can escape from the accretion disk as a relativistic jet. So we're seeing on the right here, the jet of M87. We also use observations in different wavelengths to be able to see the full picture of the object and understand more about it. So in the M87 example, the radio and optical images on the top line up really well. But when we look at this image, just going back to this slide, we see that the radio contours overlaid over the optical image from Hubble give us different information about this system. So we really need to look in multiple wavelengths to be able to fully understand what is happening in an observation. So before I go any further, I just want to give a brief overview of what is happening when an object is lensed. This is a very big simplification of what is actually happening, but it's good to have just a general idea. So we have our source over here, and that's emitting light in all directions. And without being lensed, we can just trace back here over to the observer, and we would just see the source out here. But with a lens in the center here, the light that is being emitted from the source is actually going to be deflected by the gravitational field of the lens. And these light rays are going to reconnect back at the observer. And we can trace these deflected angles back, and we see two images, out here in the source plane. And with a spherical lens, we're just going to see two images, but if we have a different mass distribution of the lens, we can see 4 images, and that's what we're looking for when we're using this method. And the number of images that we see is determined by the caustic curves, which we get by creating a mass model of a lensing system. And again, what goes into actually calculating these caustic curves is very complex. But the important thing here is that crossing a caustic either creates or destroys a pair of images. So starting on the outside of this elliptical caustic here, if we have a source out here, we're only going to see 1 image. And then when we cross inside the inside the outer caustic, we're going to see 2 images, but there are technically 3 images, but the third image is going to be too faint. So we're going to see 2. And then again, crossing into this inner caustic, we're going to see 4 images. And those are the sources that we're looking at. And really close to the inside of this inner caustic, we see massive changes in image position with just small changes in source position. So zooming in on this little area here, we have 6 sources separated by 1 milliarcsecond each. So we could think of this as potentially like a jet located just inside the inner caustic. And we can see that the image separations are much larger than the separations between the source positions. So the image separations here range from 20 to 50 milliarcseconds instead of just 1. So this is a huge offset amplification that we're seeing just inside this image amplification. And the caustics are actually the reason why with that first lensed quasar, we saw a jet coming off of part of one image and not the second image. So the quasar is located just inside that elliptical outer caustic, and most of the jet isn't inside. So we have the image of the jet here and 1 lensed image of the quasar, and we have a tiny bit of the jet and then a second image of the quasar. So that's what we're seeing with the first quasar. So caustics are very important in our observations and explain a lot about lensing. So the effect that we're using when we're trying to resolve these distant sources is called nonlinear amplification. And when we plot the total flux magnification from a lens with the caustic, you can see that just inside this cusp inner caustic that we have here, the flux magnification jumps massively. So we're looking at sources, hopefully that are located pretty close to the inner caustic. And when we plot the offset amplification with the magnification, we see this nonlinear amplification effect. And this is strongest for offsets that are located close to perpendicular to the caustic, but we even see it when the offsets are parallel to the caustic. So this is a really strong effect that we can exploit to be able to estimate offsets of a lens system. And again, this has to be a quadruply lens system to be able to have this inner caustic. So we applied this method to the source HE0435, which was discovered in 2002 and has a redshift of 1.689. And we chose this object partly because it has both Gaia observations and Chandra X-ray observations. So the Gaia observations are measured to really close precision, which allows us to create a close mass model of the lensing system. And from that, we can analyze our system and hopefully get a closer resolution estimate of the X-ray emissions. So we start with our observed Chandra data, which is here. You can see we don't have a ton of photon counts, but relatively large amount for an X-ray observation. So we simulate the Chandra data to get more counts. And then we also use the mass model that we created using our Gaia positions to get some trial source positions. So these are the critical and caustic curves for HE0435. And you can see here we have our source position that's measured with Gaia in red, and all of our trial source positions we generated as this colorful grid here. So we're closest to this caustic. So we just generated a grid parallel and perpendicular to that. And using those trial source positions and the simulated and Chandra data, simulated and observed Chandra data, excuse me, at each trial source position, you can calculate the maximum likelihood and then interpolate that to find the confidence regions of the X-ray location. So when we do that, and we plot just parallel and perpendicular to the caustic centered at our measured Gaia source position, perpendicular to the caustic, we see this nice parabolic shape here. And these horizontal dotted lines are the 1 sigma, 90%, 95%, and 99% confidences. So perpendicular to the caustic, we're getting this nice region just inside 1 sigma. But parallel to the caustic, we're seeing these 2 regions that dip down underneath that 1 sigma region. So this is kind of an interesting effect, and we see that when we interpolate and plot the confidence regions. So we have the maximum likelihood X-ray position here, which is actually the minimum based on the way we calculated this. And we end up with 2 1 sigma regions here and here. But we do have our Gaia position at 0, 0. So we can say that it's pretty likely that our X-ray observations are co-spatial with our optical observations. So this is likely not an offset AGN, but we are able to greatly increase our resolution from Chandra. So with our 2 1 sigma regions, we're going to just say that this is an elliptical region. And we have along this long axis here, we have a 10 milliarc second length. And then along the shorter axis up here, we have 8 milliarc seconds. So Chandra's maximum resolution is half an arc second. So this is still a huge jump from the Chandra resolution. While this isn't as close as some other resolutions of this method, we're still able to greatly increase the resolution of our X-ray location. So this has been applied to a few different sources before. With BO712, that one or BO712 and B1608 were both compared to radio and optical emissions instead of just optical. And BO712 was found to likely be co-spatial with both of those emissions. But for B1608, it looks like it's possible that the X-ray observations are actually offset from the optical observation. So it's possible that this source is in fact an offset AGN. So that could be a binary or one of the other effects that I talked about a little bit earlier. And part of the reason why our confidences ended up a little bit weird is we're actually pretty far away from the caustic with this source. So as I mentioned earlier, we get the strongest offset amplification when we're just inside the inner caustic. But with this source, we're pretty far away. So we can still get the offset amplification and we're still able to use this method, but we're not going to get as high of precision because the amplification is not as great as if we were closer. And B1608 and BO712 were both significantly closer to the caustic, so that analysis was a little bit better. We also are almost equidistant from these two caustics, so we end up getting interesting effects when we generate this grid because the trial source positions here are significantly closer to this caustic than these trial source positions are to this caustic. So that's also going to cause some interesting effects when we analyze this system. So looking forward, how we can use this method, the Rubin Observatory and the Square Kilometer Array are due to come online in the next few years, and they're estimated to find around 10 to the 5 lens systems through their observations. So we can apply this method to a lot of those lens systems and hopefully find some offsets. The probability that a source is within this caustic configuration is about 2%, but with the flux magnification that we get from the lensing, that probability that we'll observe it actually goes up to about 8%. So not a giant probability that we'll be able to see these, but when we're looking at 10 to the 5 lens systems, that's still a lot of systems that this method can be applied to. And this plot shows the binary dual and offset surveys so far. And we see B1608 and BO712 plotted here. And then the blue is the Chandra systems that we can apply this method to as well. So hopefully we'll be able to apply this method to many, many source positions or many systems, and doing so will allow us to again estimate the frequency of galaxy mergers and binary AGN throughout the universe's history, which will help us again understand the formation of large-scale structure, galaxy structure, and potentially even black hole evolution throughout the course of the universe's history. And I just want to finish up by saying thank you to Dan Schwartz and John Wardle at Brandeis for their help with this project. I had a lot of fun working on this, and I am happy to take any questions if you guys have them. Thank you.
Thank you very much, Alysa. Very interesting talk. So do we have any question for Alysa from in-person audience or on Zoom? You can raise your hand on Zoom and we will let you speak up. So maybe I ask a quick question at first. So talk about, I mean, tell us more about your next step in Wheaton.
The next step on this project?
No, I mean your next step as a PhD.
Oh, as a PhD. I'm not entirely sure yet, actually. Yeah, I'm sort of hoping to explore a few different things and just see what I'm interested in. Yeah.
Sounds good. We have one question from the in-person audience, please.
So when you say Rubin is expected to have 10 to the 5 lens images?
I'm sorry, I wasn't
Sorry, just a
able
moment.
to be here.
Just a moment.
Hi, can you hear me?
You could maybe just come up to it.
Yeah. Hi, really great work. So when you say that Rubin is going to have like 10 to the 5 lensed images, do you expect all of them to be AGN, or what other objects can you expect to be magnified in this way? And have you been thinking about those science applications?
So at high redshifts, they're pretty likely to be AGN just because they're so distant that they're going to be really faint unless they're super luminous. Yeah, so I'm not exactly sure how many of those will be AGN, but yeah, if that answers your question.
Thank you. Do we have further questions for Alysa? Okay, if not, let's thank the speaker again. And good luck on the debate today. And so our next speaker is Dr. Ruoyu Liu, and Dr. Ruoyu Liu pursued his doctoral degree during 2012 to 2015 in the University of Heidelberg. After that, he worked as a postdoctoral researcher at Max Planck Institute for Kern Physics. Then the Deutsches Electron Synchrotron, and went back to China as a researcher professor at Nanjing University in 2019. His research focused on the high-energy astrophysics, including the arranging of high-energy cosmic rays and neutrinos, and the candidate sources of these particles, such as pulsar wind nebula and gamma ray burst, AGN jets, and Extra. He serves as one of the physical coordinators of the Lasso collaboration. And today he will tell us about the ultra-high-energy gamma ray observation sources revealed by the Large High Altitude Air Shower Observatory. So please take it away, Dr. Liu.
Okay, thank you for the introduction. And it's my pleasure to talk about Lasso and its recent result here. Okay, so when we talk about high-energy astrophysics, usually we talk about photons, detection with photons above keV energy, is say X-ray and gamma ray. When the energy goes beyond 0.1 MeV, usually we call it enters the gamma ray regime, gamma ray astronomy regime. And when the energy when it goes like 3 orders of magnitude higher, then we call it high energy or very high energy. And so the ultra energy gamma ray is defined as the photons with energy above 100 TeV or 0.1 PeV. So at this high energy, the photon is, I mean, the source is quite rare, and usually we don't expect to see the gamma ray photons from source too far away, because at this energy, the extra galactic background light and the CMB photon will absorb these energetic particles, energetic photons, and limit the this observation horizon to a very nearby universe, mostly in our galaxy. So the mechanism to produce this ultra energy gamma ray photons are basically we have two ways. One is the hadronic channel, and then the other is the leptonic channel. In this hadronic channel, that we have the energetic protons or nuclei. It interact with a dense gas and produce pions. The neutral pions will decay into two photons, each of which will take away about 10% of the energy of this parent proton. So if we observe a 100 TeV photon, it means the parent proton most likely have energy at 1 PeV or 10 to 15 eV. For this leptonic channel, usually we have energetic electrons, and it's upscattered the photons of some low energy regional field. For example, the CMB, which is permeating throughout the universe, and the upscattered photon can reach very high energy if the electrons energy is high enough. So this figure shows the relation of the mean upscattered photon energy and the parent electron energy. We see if the upscattered photon reach about 100 TeV, then the electron energy usually is above 300 or 400 TeV. So basically, we can consider the ultra energy gamma ray emission is a probe of this PeV particle accelerator. Okay. Sorry. As such, this ultra energy gamma ray photon can be used as a probe of this probe of source of cosmic rays, which was firstly discovered by Victor Hess. And because these cosmic rays, they are charged particles. When they propagate from their source to our Earth, the intervening magnetic field will deflect their trajectory. So we cannot trace back the arrival direction of the cosmic ray to find their source. But if they produce some gamma ray emission inside the source or nearby the source, then these photons, because photons are neutral, so they will go straight toward us. So if we can pinpoint the source of this ultra energy gamma rays, then we can find out the origin of the cosmic rays, which will help us to solve this century-old puzzle of the cosmic ray origin. Also, this ultra energy photons, they represent some. Most likely they arise from some very extreme, very energetic physical processes in the universe. So it's a probe of the so-called long-thermal universe and help us to understand the physics in this extreme conditions. Also, this energy of this ultra energy photons and their parent particles they have energy beyond the maximum energy that can reach in the man-made accelerator. So it's also provide us a way to learn some new physics if there's any. Okay, so among many astrophysical objects in the universe, there are some of them are frequently considered as the potential sources of ultra energy gamma ray. In our galaxy, inside our galaxy, for example, the superlunar remnants, the Pulsar Nebula, the massive stellar winds, they are usually considered as they're powerful enough to accelerate particle to PeV energy and produce the ultra energy photons. SNR have strong shocks. Also, Pulsar wind have very powerful electron position winds, and they can produce also this very strong termination shocks. And the massive stellar wind also they are have this the collective or many this OB stars, the stellar wind that can also drive a strong turbulence or strong shocks. And outside our galaxy, there are many more possible sources. For example, the merger shock formed in the structure formation, and also this relativistic jet in the blazars or some other process in this long blazar AGN, and also in star forming or starburst galaxies, there could be very energetic like also superlunar remnants or or this gamma ray burst, they can also produce energized these particles to very high energy and produce this photon. But as I mentioned earlier, so because of the absorption of ultra-energy gamma rays due to by the cosmic infrared background and the CMB, this source must locate within maybe a few megaparsecond or a few tens megaparseconds to make the photon can reach us. To observe ultra-energy gamma rays, well, it's a bit different from the in lower energies because the atmosphere is opaque to this energy. For example, when a photon with very high energy enter the atmosphere, it will interact with the electric field of this nuclei via the space heat process, and it will be absorbed and produce electron-positron pairs. And these electron-positron pairs, they are still very energetic, then they will radiate gamma ray again via the Bremsstrahlung processes. And so such kind of a E gamma cycle will repeat many times and produce many more secondary electrons, positrons, or gamma rays, and formed a shower. We call it the extensive air shower. So we have to collect all these secondary particles on the ground to then to reconstruct, to derive the property of the this initial photons. So this is like an indirect detection. We cannot detect it with satellites because, as I said, this high energy photons, they are very rare. So we need a quite large collective area to get sufficient statistics. So it's impossible to build such a large detector as a satellite. So we must detect it on the ground. It may be also worth noting that in addition to gamma rays, so cosmic ray, like cosmic protons or nuclei, they can also initiate these air showers and produce many secondary particles. Because cosmic rays, they are bombarding our Earth every time, all the time. So actually, these showers, the shower event is actually dominated by cosmic ray induced showers. The only difference is that the cosmic ray induced air showers, they usually contain not muons because they are hadronic. They are hadrons, so they can have these hadronic interactions with the nuclei and produce charged pion. A charged pion can decay into muons, which is a very penetrating particle and can reach the Earth. And this will be very important to distinguish between this gamma ray induced shower and a cosmic ray induced shower. So this picture shows the Lasso, this instrument. So in this center, we have this water pool, which is called the Water Cherenkov Detector Array, or WCDA. It consists of 3 parts, 3 water pools, and each of them are divided into many cells. In each cell, there is a PMT. When the secondary particles enter this water pool, it will produce Cherenkov light, and this PMT will collect this light. And based on this information, we can reconstruct the injected the initial particles. It's a species and its energy and direction. This WCDA usually generally works between 1 TeV to 10 TeV. And so if you look closely here, you see some this blue square or something. This is called a wide field Cherenkov telescope array. It's actually this 18. There are 18 telescopes here, which aims to detect the Cherenkov light of the secondary particles generated in the air. It mainly aims to detect cosmic ray, like cosmic ray protons or nuclei, but it can also detect gamma rays. So it looks like it's just put it randomly here, but actually each telescope is pointing to a different direction. So they will cover the all sky, the full sky, to monitor monitor the full sky. And the rest of the array are composed of the, you see this this piles of soil here. Under each this piles there is one muon detector. So in total we have like about 1,200 muon detectors. And we also have this shown as this white dots here. These are electron detectors. So electron detectors, they are meaning scintillators. So when this secondary electron or position reach the Earth, reach the ground, it will detect them. And the muon detector actually are some there's a water bags and also PMT here. When it is buried inside the under the soil, because we want use the soil to absorb these electron positions or gamma rays, and only let the muons go inside. So in this way, we can know whether this shower is induced by cosmic rays. Because if it is induced by gamma rays, we do not expect much muons in the shower. So for example, if a shower comes in this way, this arc shows the its front, then it will ignite many different muon detector or electron detectors. Then we can collect the information from all this ignited detector to reconstruct its energy. So this kilometer square array, or KM2A, usually works above 10 TeV. So our topic today is mainly about the results from KM2A. So this figure shows how do we distinguish between gamma rays and the protons. This is from the simulation. We can see we can define some quantity, basically representing the ratio of a muon number to the electron number. So from this simulation, we can see if the shower is induced by gamma rays, then this ratio is usually lower than 0.01. But if it is induced by protons, then this value is usually larger than 0.1. So we can use this value, 0.1 as a simple cut to reject some protons, because when we want to detect gamma rays, then protons will serve as the background. So this figure shows an example that this is the practical data detected throughout the Crab pulsar direction with a window with over a 1 degree radius. So this red curves shows the gamma rays from that direction. Basically, you can consider this as the spectrum of the Crab nebula, and this black curve shows the cosmic ray events. Oh, sorry, I forgot to say this y-axis is the number of the events detected per hour. So this is like the cosmic ray events detected from that direction. You can see it's two orders of magnitude higher than this gamma ray signal. So if we do not figure out a way to remove this background, we can never extract useful information of the gamma rays. So when we apply this cut onto this background, then we got this blue curves. You can see it's reduced by a lot. Above 100 TeV, this background rate is reduced by at least 10,000 times, or it could even reach 100,000 times at like 300 TeV or above. So this gives a quite low background level and makes this detection even as a background free. I mean, if you goes to this above this 100 TeV, and this so this results in a very good sensitivity of LHAASO. You can compare the LHAASO sensitivity here, shown as this gray curve, with other this gamma ray detector, high energy gamma ray detector. This is the CTA source, and this is a Hawk with 5-year exposure. So basically, this reason is that we have like a large collection area, and and second is we have this muon detector, and then we can apply this muon cut rejection method to the background. Okay, so this is the first result of LHAASO. So this is in galactic coordinates. This white region is outside the LHAASO's field of view. In this first discovery, we use the data of half LHAASO array, because at that time only half array is constructed, and the observation time is about 11 months. So all the sources here are above 100 TeV. The significance reaches at least 7 sigma. So there are 12 sources here. One is this famous Crab Nebula, and the other, the other are, or actually there are also many of them are famous sources in its high-energy astrophysics field. So here are the list of these sources. We can see the maximum energy here. The highest energy we detected is 1.4 PeV. This is from the Cygnus cocoon region, which is a very famous source detected by Fermi and other detector. And also another, actually we have also one more photon with PeV above PeV energy. This is from the Crab Nebula here, and other, you can see other maximum energy are all, like most of them are like 300 or 400 TeV here. And we also try to find out some possible counterparts of these sources. Well, most of them are related to pulsars or circular remnants, or you can also see this. Some of them are related to this young massive star cluster marked as YMC here, and these sources are also previously detected at the TeV or GeV energy here. I just want to mention that we among these 12 sources, we also detect one new sources they have never detected before in high energy band. We also try to find some astrophysical counterpart, but we didn't find any inside its area. So detection of this source may imply there are much more such kind of energetic particle accelerators hiding in our galaxy that has never been detected before. Okay, so this just shows the three main astrophysical objects that are related to these 12 sources. As is pulsars and the circular remnant and these young massive star clusters. Here shows the SED, the spectrum of three brightest sources at 100 TeV. Actually, Crab Nebula is not the brightest one at 100 TeV. The brightest one are these three. They have some common feature. For example, we see the spectrum has a gradual softening with increasing energy. Here we fit it with the log parabola function. We find it have a better fitting with this single power law function. And second, although it shows this gradual softening, but we didn't see a clear cutoff here. So it means the spectrum could even extend to much higher energy, but we just don't have the sensitivity to detect them now. But waiting for maybe a few more years, we can detect higher energy photon from these sources. And another common feature is that these sources are, this region are very complex. There are more than one potential sources for them. For example, in this G2226, in this source, there is a energetic pulsar, and it drives very bright pulsar nebula called the Boomerang Nebula, and also it's associated with the superlunar remnant called G106.3 plus 2.7. Both of these two sources can, in principle, produce these gamma ray emissions. In this region, also there are some molecular clouds in this region, so it makes this hadronic arranging of this gamma ray emission possible. So in principle, both leptonic arranging and the hadronic arranging are possible for this ultra-energy gamma ray emission, and also with either the pulsar nebula or the superlunar remnant could be the true source, or both of them have some contribution. So here is the example for this middle source G 1908. We fit this multi-wavelength gamma spectrum with leptonic model shown as this dotted dashed curve, and also fitted with the hadronic model. So both of them can fit, and we cannot distinguish with the current data. Another thing worth noting is the last measurement on the Crab nebula. So this Crab nebula is the only source with a definite astrophysical counterpart. So it's the Pulsar nebula driven by the Crab pulsar. In here we show the SED from X-ray to PeV energy, and we fit it with the so-called standard one-zone model. Just put everything, we assume everything together, and each this physical quantity, like magnetic fields, like the radial field, is homogeneous inside the source. And we use this electrons synchron relation to fit the X-ray to MEV emission, and use the inverse Compton of the same population of electron to explain the GeV emission to PeV. It can be seen that this model can fit the spectrum well, but this one model may be unphysical because we have this observation of this so-called Crab flare in MEV and GeV band by RGD and Fermi-LAT. So they have this flare only the shortest one lasted like just a few hours. So it means there is a very, very compact region with very high magnetic field, so it can cool this emitting electron very fast. So inside this Crab nebula, there must be more than one radiation zone here. So there can be other explanation to these sources. Sorry, one thing I forgot to say is that if we analyze based on this one-zone model, then we can obtain this acceleration efficiency to 0.14. This acceleration efficiency is defined as the effective electric field over the magnetic field, because in astrophysical environment, usually the electric field is induced from the movement of the magnetic field. So this value cannot be larger than 1. So in this case, if we want to explain this 1 PeV photons with this inverse Compton radiation, and in the meantime to use a synchrotron radiation to explain this low energy data, then we need this value is close to at a level of 0.1. This actually is a very, very high value. For example, in the galactic supernovae remnants, this value is usually 10 to minus 5 or 10 to minus 4. So we can see how extreme the pulsar the Crab nebula is. So if sorry, this I should firstly talk about this. So if we relax this one-zone model and consider there could be a second electron or hadronic component inside the Crab nebula, then this condition can be relaxed. We don't need such high this acceleration efficiency. For example, if we have a hadronic component here, like if the Crab nebula also accelerates some protons, then the hadronic emission can explain this highest energy points, while the maximum electron energy just have an earlier cutoff here. Okay, I want to use the just last 1 or 2 minutes to talk about this galactic diffuse gamma emission. So this figure shows the sky viewed by Fermi-LAT at above 1 GeV. So we can see the most prominent structure is this band associated with the galactic plane. So this actually is produced by the interaction between cosmic rays and the gases in our galaxy, such as the molecular cloud or this H1 cloud inside the galaxy. This is called the diffuse gamma emission in the plane, and this component this emission actually extends to much higher energy. It's not only limited to GeV band. Last year, the AS gamma experiment, they report the discovery of this sub-PeV diffuse emission from the galactic plane. And if they extrapolate the expected spectrum from the cosmic ray interaction, you can see there is some insufficiency to explain the highest points. LHAASO actually also try to find this this diffusive emission, but we something different is that we used a larger mask radius for these sources here. We as this, so we consider we consider this the size of each source and the PSF of the detector. So so the mask region is much larger than what AS gamma did. AS gamma used 0.5 degree. It's a fixed value to mask the region around each source, but we use a larger mask radius. And to do this, we find out there are some diffuse emission from 10 TeV to close to 1 PeV. And these gray dots are the flux mirrored by AS gamma. We can see our result is systematically lower than AS gammas, but although at this last 2 points, they are still consistent within the error bar. So this difference could be explained as this different mass radius. But we also, I mean, for the moon, we are also not sure whether this mask radius is appropriate. I mean, whether the contamination from this extended source are all removed. Okay, so let's go. Okay, sorry, I exceed the time. So so this is the summary. Basically, I just want to say the ultra-energy gamma ray astronomy is a new window to understand the extreme universe, to understand some very energetic processes. And LHAASO has an unprecedented sensitivity for ultra-energy gamma rays, and it has detected dozens of ultra-energy gamma ray sources with the highest energy beyond 1 PeV. And the spectrum of Crab nebula extend to 1.1 PeV and implying extremely particle accelerator operating in its center. And it also shows a possible indication of an additional spectrum component above 700 TeV. And the galactic diffuse gamma ray emission in 10 to 1000 TeV has been detected by LHAASO. But the influence of the extended source has a large uncertainty, and we need more time to understand whether we deal with this diffusive gamma ray emission properly. So we now have several working groups working on different topics, and please stay tuned. And thank you for your attention.
Thank you very much, Dr. Liu. Do we have any questions for Dr. Liu? So, yeah,
I do. Very exciting talk. A couple of questions. Is there any hint about this new LHAASO source without any low energy counterpart, galactic or extragalactic or other? Second question, you talked at the beginning about inverse Compton over the CMB only. Of course, you can use also the synchrotron radiation inside the source and inverse Compton on that one. Is there any source for which you can use modeling with synchrotron self-Compton to constrain the magnetic field inside the source, beside the Crab, and how long would it take you to constrain the magnetic field? How many years of observations do you expect to need for that?
Okay, so first about this source, actually we try to analyze this region in Fermi-Let data. We find some emission there, but it's not. I mean, from the spectrum, it looks like a pulsars radiation. So it could be a pulsar, also a pulsar nebula here, but we didn't see any. This pulse emission or the period of the emission, so it cannot be confirmed. Also, in this region, there are also this source is associated with some molecular clouds, so it could be also a hadronic radiation here. So for this source, currently we don't have sufficient information to have a further judgment. Okay, so, and then for this inverse Compton emission, yes, in principle, we can this electron can also upscatter this synchrotron radiation to produce ultra-energy gamma ray emission. But if the magnetic field is high, then I mean then the synchrotron radiation they have I mean they peak at a high energy. The problem then is that the Kalinin-Shina effect will work to reduce the cross section for the scattering and makes the spectrum drops very quickly. So CME has a low energy, so the Kalinin-Shina effect is not so important, and so I mean we have tried that usually for reasonable parameters, usually this inverse Compton with CMB dominates above like 100 TeV.
Thank you.
Thank you for the question.
Do we have further questions for Dr. Liu? Maybe I have one very quick one. So just for curiosity, so in your first catalog release, most of the all of the sources are galactic sources. Do you expect to see any extra galactic source in the future, multi-years run from LHAASO?
I hope so, because you know, if we can detect it at a lower energy, but if you talk about beyond 100 TeV, then this source must be very nearby. Actually, there's not much many candidates. For example, M82 may be possible. Because it's radius is only 3.5 megapasecond, so the absorption distances maybe absorption is not so severe.
So I think thank you, Dr. Liu. I think I saw a raised hand. Brandon, please unmute yourself.
Yeah, hi. Sorry. Yeah, I had a quick question with regard to searches for transients. How far have you gone, or what sort of what number of potential transient TeV sources have you been able to try and match up with different catalogs at this point? I imagine it's a work in progress, but it's something I'm quite curious about.
Yeah. So for KM2A, it's very hard to find any transients because you know it works at a very high energy and the photon counts rate is very low. So usually we need to collect a long time and to get sufficient statistics to claim it's a source. So most likely it's impossible for us to see it's a transient. But we can do this with this WCDA. It works actually it can works at as low as 100 GeV. So one of the scientific goal for WCDA is to detect the like gamma ray burst or the AGN flares. So maybe this is at the low energies it is possible, and we have working groups for gamma ray burst, but currently we have not detected any. I think we need some luck.
Yeah, no, definitely a lot of luck. But sorry, what was your low energy threshold again? You said 100 GeV?
Yeah, 100 GeV. It could be even lower, but requires some specific, you know, this analysis. Generally, you can consider it as a 100 GeV.
Thank you.
You're welcome.
So do we have further questions for Dr. Liu? If not, let's thanks both speakers again.
Thank you.
And thank you very much for coming to the seminar, and see you next week.
Bye-bye.
Thank you.
Bye.